class is related to the fundamental relations of different reactor system, the rate of reactions, and degree of conversion, what we normally use for chemical reaction engineering. So principally we'll discuss about what is the understanding on the rate of reactions, the degree of conversion, particularly in different kind of reactor system. Particularly we'll be focusing on batch reactor, CSTR model, which is actually mixed flow reactor, and plug flow reactor model. So basic understanding of all those topics we'll be covering first. Initially we'll be discussing what is the relationship between the concentration of a reactant, the fraction conversion, and the volume expansion factor eta model of the reactor systems, particularly CSTR and plug flow reactor model performance equation. That is very fundamental and useful also. We'll discuss and we'll derive all those relationships in coming slides. So the fundamental description is very important because you need to understand what is the relation between different form of equation. One equation may have different form. So whenever we are talking about any rate of reaction, we need to understand that the unit is always fixed. Mole per liter per hour, or maybe gram per liter per minute. Anyway, the amount, volume and time, the three components will be there. So essentially whenever you are writing any rate equation, we need to know that it is actually 1 by V dNA dt. This derivation is actually always valid and always correct, because we need to understand the DNA is the number of mole changing with time, N is mole, gram, absolute mass, and V is the volume. Maybe at that time when you are calculating the rate, that time what is the change and what is the volume, those aspects will come over and for calculation of the rate of reaction. This above definition is always correct. Whatever may be reactor, whatever may be the scenario, this definition is always true. But we will have some special case also, which we normally remember and we memorize the special case scenarios, that is RA equal to dCA dt. It is the change of concentration with time. So we need to understand what is the original definition and what is the special case. Here dCA dt, because if the volume do not change with the reaction system, and then we can say the Na is actually concentration into V. So differential dV equal to 0. So essentially if I make Na equal to Ca into V and make that differentiation, it will become dCA dt, and we will also have dVdt. Anyway, dVdt component is 0, so essentially it is becoming dCA dt. It is a special case scenario when volume remain constant. Similarly, for fractional conversion, we need to understand what is fractional conversion, what is the definition of it. It is actually very simple. For example, we are starting with some Na0 number of molecule in a reaction process. That is the overall number of molecule present in the whole entire system, and after some time or maybe in a process the number of mole is decreased to Na. So fractional conversion is how much mole is lost with respect to the initial mole. So essentially when at the time of reaction or maybe no mole has been changed, then fractional conversion is actually Na and Na0 is same, so it is 0. And when all the molecule has been converted, that time Na equal to 0, so essentially fractional conversion equal to 1. So the definition is always true. You need to understand the definition is in terms of number of mole, number of molecule, not related to concentration, because concentration can change. And if we are going to say about volume change in reaction, then we need to understand that is actually eta xa. Eta is actually going to give us the idea how much volume change will happen once the whole reaction is complete. I mean to say when Xa equal to 1, when complete conversion of one reactant to product has happened, then what is the final volume, what was the initial volume by initial volume. So fractional change in volume When xa equal to 100% conversion has taken place, that value is actually fractional change in volume or eta a. This definition is also true, always correct, which can be simplified a little bit: v by v0 equal to 1 plus eta a xa. So this relationship, whatever we have highlighted, for example, R equal to this one, XA definition, what is the final fractional conversion, or eta, all those definitions are always valid for any kind of scenario. But for example, in this case, when you are talking about RA equal to dCA dt, this is only special case scenario when volume is constant. So we need to discriminate, we need to understand the differences between them. We need to have some other derived relationships as well in this class. First one is, what is the relationship between XA and CA? Of course, depending on the scenario, the picture can change, but basically we know that XA equal to the fraction converted rather. So that is initially minus NA by initial value that we have already shown you. And if we divide by initial volume V0, so we can see so this term is also divided by V0 here. Na is also being divided by V0, so Na by V0 and Na0 by V0. Now we can see that is actually, we can actually a little bit simplify. So Na0 by V0 means initial concentration, so Ca0. Here also it is Ca0. Na by V, we are just adjusting it, Na by V into V by V0, so Na by V will become C. So this part is C, this one and this one is actually C0. So we can simplify it, Ca0 minus Ca into V by V0 into Ca. So essentially now we can again write Ca0 minus Ca, V by V0 equal to 1 plus eta a xa. So now we can summarize similarly xa and here. So this expression, if we put together, we can rewrite the expression Ca0 into xa equal to Ca0 minus Ca into Ca eta a xa. Now this equation we can rewrite in both the way. First one, for example, in this case, we are Ca0 part we are putting it and Cxa we are putting it right side, and the whole block we are bringing in left side, so rearranging, and we can say Xa equal to Ca0 minus Ca divided by Ca0 plus Ca eta a. This is expression of Xa in terms of Ca. We can do the opposite also. From the same equation we rewrite it, Ca into 1 plus eta a xa, so it is becoming Ca0 1 minus xa. Just check how we are making the expression here. So this whole block we are putting this side, so this thing is coming here and these two things is rewritten here, and which can be finally adjusted to write Ca by Ca0 equal to 1 minus Xa by 1 plus eta a xa. So these two equations are actually equivalent, they are, and these two equations are also always valid. So when we know Ca, we can rewrite in we can calculate Xa from Ca, or opposite way we can convert Ca in terms of Xa. Whichever we use for depending on the equation can be useful for our analysis. So this is the very fundamental definitions what we need to know, or we'll say the fundamental relationships which can be useful for our upcoming derivations.